A specific type of bounded a space of bounded and linear operators is called the dual space. So the dual space of a norm vector space X, denoted by a prime, X prime, is the set of linear and bounded operators from X into R. And the notation prime will be justified later. In some texts or references, the notation is denoted by a star. And this is also a reason why a star has used. But for now, we know that even though the primal space, that is this vector space X, the norm vector space X, is not complete, the dual is always complete. So X prime is a Banach space with the operator norm. And in this case, the operator norm would be, so if I have, let's say, an X prime in the dual space, the norm in capital X prime is equal to the sup of X prime of X. Here, the norm is now taken with respect to the norm of R, the absolute value, okay, for any X in the closed unit wall, okay, of capital X. So you can alternatively use the other definitions of the operator norm, but for now, let us use this specific formulation. So again, even if the primal space X is not complete, the dual is always complete according to the previous theorem, stating that here our codomain is R, and we know that this is a Banach space. Therefore, the dual space of any vector space is complete. To justify the notation of prime for the dual, let us consider the space, the dual space of R. So by definition, the dual space of R is the set of all operators T from R into R, such that, so first this operator must be linear, okay? And since the domain is a finite dimensional, it follows that all linear operators from R into itself is bounded. And as we have discussed last time, linear operator between R into R must be of the form for some real number M, T of X must be equal to mx for all x in R. So from here, one can easily check that the map at, say, J from R prime into R defined as follows. So J of, let's say, and let us put a subscript T sub M, okay. J of T sub M is equal to M. This one is an isometric isomorphism. So one can easily check that the norm of Tm is equal to M, and therefore this is an isometry, and it's clear that this map is surjective. Since an isometry is always injective, therefore J is an isomorphism. So here, the prime is justified from the fact that M would be the derivative of your linear operator T sub M. Okay, so that is the justification of the notation, the prime notation for the dual space. In particular, the dual space is isometrically isomorphic to the space R. This is in fact valid for general Hilbert spaces. And we will discuss this in the succeeding lecture. Here's another example. Let us consider functions in Lebesgue spaces. So let P and P prime. So P prime is the dual exponent of P. That is the sum of the reciprocals of P and P prime is equal to 1. Okay, and consider, let's say, an open set Rn, or we can take a measurable Rn, omega subset of Rn. Given, let's say, a function g in LQ prime or LP prime of omega, a real valued function, okay, let us define the map T sub g defined from LP into R, okay, as follows. So it takes a function f in its domain. So here f is in LP, and it takes the integral of the product of f and g with respect to the Lebesgue measure. Okay, now if we apply the Holder's inequality, we know that the absolute value of the integral of the product is less than or equal to the norm of f in LP times the norm of g in LP prime. And this implies that, okay, according to the definition of a bounded linear operator, T sub g is a bounded linear operator in LP omega into R, which is, of course, by definition, the dual space of LP. So that's LP prime. And the norm of T sub g in the dual space of LP is less than or equal to the LP prime norm of your given function g. Okay, so in this case, given a function g in LP prime, you can find an element in the dual space that satisfies this property. Now, the question is, can we improve this inequality to an equality? And one would like to ask, given an element in the dual space of LP prime, is it possible to represent the element in the dual space by such an integral for some g in LP prime? Well, the question is affirmative, depending on the values of p. And we will discuss that in detail in future lectures. But for now, here we see that given a function in LP prime, we can assign a map T sub G in the dual space of LP. And we will show that later if P, let's say, is strictly greater than 1 and it is finite, this correspondence is in fact an isometric isomorphism. So to close this section on bounded linear operators, let us discuss the following theorem. So the following is topological property for the set of all bounded linear and invertible operators from one Banach space X into another Banach space Y. So let X and Y be, let's say, norm spaces, and L iso sub iso is the set of all bounded linear operators from X into Y that are isomorphisms. So linear and bijective. They are linear, bounded, and bijective. Then this set is open in the space of bounded linear operators from X into Y. So we will prove this in several steps. The first step is the so-called Banach inverse theorem. Which states that if T is bounded and bijective, in other words, it is an isomorphism, then the inverse, which exists due to assumption, is also bounded. So for the proof, we will discuss this later in future lectures. For the proof, we need several theorems, in particular the open mapping theorem in the future. So for now, let us accept this as a fact that a bounded linear invertible operator has also a bounded inverse. The second step would be the following. So let's state this as a theorem. Let us consider a bounded linear operator from X into itself. And for simplicity, if the domain and codomain are the same, we will just use this notation. L of X, the set of linear and bounded operators from X into itself. And suppose that the limit superior as n goes to, or as m goes to infinity, of the norm of T sub m divided by, or raised to the power 1 over m. If this is strictly less than 1, and this is called, by the way, the so-called spectral radius of your operator T. So if the spectral radius is less than 1, then the Neumann series let us denote that by S. This is the sum of the powers of t. So this is similar to your geometric series, but here the terms are now operators. Okay. Then this Neumann series, or geometric series if you like, is also bounded. And it is an isomorphism with inverse, which is equal to the identity operator in X times t minus t. And obviously this is also bounded, of course. Since the identity operator is bounded and t is bounded by assumption. So the term spectral radius will be emphasized or will be discussed in detail later when we discuss, when we deal with the so-called spectrum of a linear operator. So when we talk about a spectrum, for now, you can think of eigenvalues of matrices. So this spectral radius would be, let's say, the largest magnitude of the eigenvalue, of all the eigenvalues. So let us prove this theorem. So to start, according to the assumption that the spectral radius is less than 1, there exist two numbers, let's say, r between 0 to 1, and a sufficiently large index, a capital M, such that the norm of t sub m, the norm of t raised to m, is less than or equal to r raised to m. So for sufficiently large indices, this must be less than, strictly less than some number r, strictly less than or equal to some number r, and this number r is less than 1. So you basically apply the definition of the limit superior. And of course, the index must be greater than or equal to capital M. And let us denote S of k to be the partial sums of your Neumann series. So we cut off the sum up to the power k. And since the composition of bounded linear operators are bounded, and the space of bounded linear operators is closed under addition, so this is also bounded. So what we do, so to prove the convergence of this Neumann series, it is enough to prove that this is this sequence of partial sums is Cauchy. So for this, if L, let's say, is greater than K, then let us take the difference of two partial sums. This one, so taking the norm, the operator norm. So here, you need to take the sum from K plus 1 to L, T to the M. So the terms 0 to K, since K is less than L, will be cancelled. Applying the triangle inequality and the fact that the operator known is sub-multiplicative, this is less or equal to the following sum. So we can put the norm inside according to the triangle inequality, and then you take the norm of each tm times. Okay. And this is less than or equal to according to the first statement r to the n. And this is, of course, tends to 0 as L and K tends to infinity. So the sequence of partial sums is Cauchy, hence S, which is the Neumann series. And by definition, this is the limit of partial sums exist. Since it is Cauchy, okay. So the limit exists in Lx by completeness of Lx. And for this, of course, we need that X is a Banach space. A Banach space. And I need to correct the assumption later. So this must be Banach spaces as well. Okay, so the completeness of the space of bounded linear operators from X into itself yields that this Neumann series exists. Now, to prove that I minus t is in fact the inverse, you just follow the idea for the case of your usual geometric series. So indeed, we have, okay. So if you wish to verify that this is the inverse of S, the goal is to show that this is indeed the identity. Okay, so from this, this is equal to the limit as k goes to infinity of the partial sums. And you will see that this is sk times the identity. So you get your partial sum minus, so multiplying by, let's say, by t, you increase the power by 1. And of course, re-indexing, the index here now will start at 1 and end with k plus 1. So you have a telescoping sum. So this is what? The identity minus t raised to m plus 1. This is equal to 0. And I should replace this by k plus 1. I should say this is the identity, since the limit as k goes to infinity of t to the k plus 1 is the 0 operator. This comes from the fact that you have this estimate here. So if you pass m to infinity, or you replace m by k and pass k to infinity, and taking note that r is less than 1, the right-hand side will tend to 0. Okay, so that is the case. And you can, of course, do the same process to show that I minus t times S is also the identity operator in L of X. This shows that I minus t is the inverse of your operator S. And this is what we wish to show here. So again, if the spectral radius of your operator is less than 1, then it follows immediately that the Neumann series S here is invertible, and you can in fact determine the inverse by the identity operator minus the operator T. So, corollary or remark, I should say. The previous theorem also holds, or the conclusion of the previous theorem also holds if the norm of T is less than 1. It's less than 1. Okay. Indeed, you can show this as follows. So taking the norm of T sub M, okay, Lx, this is less than or equal to the norm of T raised to M according to the submultiplicativity of the operator norm. And if we raise this both to the power P, power M, 1 over M, so we have this estimate. And taking the limit as superior, both sides. So but by assumption, this is less than 1. Okay. So if the norm of your bounded linear operator from X into itself is less than 1, then this implies that the spectral radius is also less than 1. Next, the final step, or the second to the last final step, is the following. So we claim that if, let's say, T is an isomorphism, it's a bounded isomorphism from X into Y, and S it's a bounded linear operator such that the difference of the norms is less than the norm of T inverse. This is well defined according to step 1. Since according to the Banach inverse theorem, if you have an isomorphism, a bounded isomorphism, then it is the inverse is also bounded. And of course, the bounded is not, the inverse is not equal to 0. So the norm exists and it is not a 0. If this is satisfied, then S is also a bounded isomorphism from X into Y. So accepting this fact at the moment, we now complete the proof of the theorem. So from step 3, so given, let's say, a point in the space or in the set of bounded isomorphisms from X into Y, we know that the ball centered at T having this radius, okay, so this basically describes the set of points in the open ball with respect to the space of bounded linear operators, of course, centered at T with radius this reciprocal. So this is a subset of L iso. Therefore, given any point in L iso, you can find a ball centered at that point in L iso as well. So this means that, according to the definition of an open set with respect to the metric topology, this is open in the space of bounded linear operators from X to Y. So the proof will now be done once we have established step 3. Okay, so let us prove step 3. So we need to show that if S satisfies this property, then S is an isomorphism. Since it is bounded by assumption, it suffices to show that it is invertible, an isomorphism. So we show that S is an isomorphism, and for this, we can write S as follows. So S is equal to, let's say, T minus T minus S. Okay. So here we write S using this information here in terms of T minus S. So to compensate that, we need to subtract this from T. And furthermore, okay, according to the Banach inverse theorem, since T is an isomorphism, T inverse exists and it is bounded. So here we will have first we factor T minus T inverse T minus S. Okay, so probably let us write this as T minus the identity T minus S. And then you write T, or you write the identity as T times T inverse, so that you can factor T both sides. So based on this, we only need to show that the second term is an isomorphism. And why is that? If the second term is an isomorphism, in this case, the inverse of S is in fact given by I minus T inverse T minus S, the quantity, take the inverse, and then T inverse. So similar to the case of matrices, for the inverse of the product, you can distribute the inverse, but interchange the order. Okay, so we only need to prove the invertibility of the second factor. And for this, take note that we have our previous theorem and the remark. So according to this theorem, if the spectral radius is less than 1, I minus t is invertible. In fact, the inverse of I minus t is equal to S. According to this remark, if the norm of your operator is less than 1, then the spectral radius is less than 1. Okay. So from those discussions, so this follows from the previous theorem, the remark, and the fact that the norm of this, okay, the norm here is taken in L of y, because this maps from x to y, and this maps from y to x. So it should be x as well. So if you apply the multiplicative property, this is the norm of t inverse times the norm of t minus s. And we have an assumption for this. This one is less than this quantity. So if we multiply both sides, this is strictly less than 1. So let us put that here. So if the norm of this operator is less than 1, then according to the previous theorem and the remark, it follows that the identity minus that operator is invertible, since the inverse is equal to S, the Neumann series. So this is the proof of step 3, okay? And now you see why this assumption is needed in order for the product of these two operator norms to be less than 1, guaranteeing the invertibility of the identity minus that operator. So this is the proof of step 3, and we already know that this step 3, according to step 4, implies the openness of the set of isomorphisms from the space of linear and bounded operators. In the next lecture, going back to our previous example, we will prove this claim here, that the dual space of Hilbert space is isometrically isomorphic to itself. So in particular, this implies that any finite dimensional for any finite dimensional vector space, norm vector space, the dual is isomorphic to itself. Since a finite dimensional vector space is isomorphic to a given Euclidean space, and the dimension is given by the dimension of the given vector space. And that is called the Ries representation theorem.